Hey everyone, last time we left off with the universal mapping property, and so let me just remind you how that goes, right? The universal mapping property essentially characterizes homomorphisms from a cyclic group to other groups, right? So it went something like this, so let's let G be a cyclic group and H group. And then there were two parts, right? In the infinite case, so if the order of little g, our generator, is infinite, then for each little h in capital H, there is a unique homomorphism phi from G to H such that phi of our generator equals H. So what that does is it tells us that for every element of capital H we get a new homomorphism, and that is it. Right? So you can say that there's essentially a one-to-one correspondence between elements in capital H and homomorphisms from G to H. And then the second part, right, in the case that we have a finite, if the order of G equals n, then for each little h in capital H, you don't have to write this down, I mean, you should already have this in your notes. For each h in capital H, there is a unique homomorphism phi from G to H, taking the generator to H, if and only if H to the n equals the identity, put a little capital H there, so it's the identity in capital H. Right, so there's the universal mapping property. And so now what this tells us is that there is a correspondence between homomorphisms in H, homomorphisms from G to capital H, and elements of H that satisfy that property right there. Right? So not quite as easy, you're not quite as free to come up with homomorphisms in the finite case. Now what I want to do are some applications. So applications of the UMP. And essentially the applications are counting homomorphisms. Right? So somehow we'd like to characterize or classify the homomorphisms from a particular cyclic group to some other group. So as a first example, how many homomorphisms from Z to Z8? Well, the answer is immediate, right? Right, so the answer is automatic. According to the universal mapping property, there are exactly 8 homomorphisms, 1 for each element in our codomain. Right? And how do they go? Who would these homomorphisms be? They would be the ones that send our generator 1 to 0, our generator 1 to 1, there's another one, generator 1 to 2, 1 to 3. So send the generator to each of the elements of Z8, and that gives us a new homomorphism each time. Now, one thing to be aware of, so let me write this as an observation, right? That's the end of that example right there, and I'm going to do more examples in a second. But first, so observation. If we have, let's write it like this. So if G is cyclic with generator little g, and we have some homomorphism, so let's say and phi from G to H is a homomorphism, then when I look at the image, right? So the image of phi, remember the image is the set of all things of the form phi of, I need to use a different symbol. How about little x, where x is in capital G. Now this is going to be equal to the set of all things of the form phi of G to the k, where k runs through all integers, right? Because x can be expressed as a power of the generator. Because this is a homomorphism, I can rewrite this as phi of G raised to the little k, where k is in Z. Now what's this? The set of all powers of phi of G. Well, that is exactly the cyclic subgroup generated by phi of G. So the image of a homomorphism whose domain is a cyclic subgroup is a cyclic subgroup, right? The cyclic subgroup generated by the image of the generator. So that will be useful to, I mean, there's nothing deep going on here. It's just using the definition of image and the definition of cyclic. I guess then we use the definition of homomorphism also, but putting those three things together tells us that the image of a cyclic group is cyclic, and it tells us exactly who the generator of that image is. So next example, let's ask this. So how many homomorphisms from Z onto Z8? Right? We know if we don't add that restriction onto, then the answer is 8. Now, if we want it to be onto, using this observation right here, what do we know? Well, then we will need, right? We need the image to equal all of Z8, which means that we will need the cyclic subgroup generated by phi of G to equal, or sorry, phi of the generator, in this case phi of 1, to be equal to a generator of Z8, right? So since Z8 is generated by, let's see who are the generators, 1, 3, 5, and 7, right? Any one of those 4 elements will be a generator. There are 4 homomorphisms, or well, let's say 4 homomorphisms that are onto, right? So why is that? If we send our generator here to a generator of Z8, then we know that the image of our homomorphism will be equal to the cyclic subgroup generated by the image of 1. And as long as we send it to a generator, then we will have that our output generates the entire codomain Z8. Another example, so let's say how many homomorphisms from Z to S4. What's the answer? Well, there's exactly one homomorphism for every element of the codomain, and so the answer is 4 factorial. Now, so let's rephrase this now, or let's modify the question. How about of those 4 factorial homomorphisms from Z to Z4, how many are onto? So think about this one for a minute now. The image of a cyclic, the image of a cyclic group is going to be cyclic. So if it was onto, That would tell us then that the entire codomain is cyclic, but we know that S4 is not cyclic. So there can be no onto homomorphism, right? So the answer here is there is 0. Okay, next, so we're just going to keep doing, we're going to do a few more examples here. So if phi from Z to Z10 is a homomorphism, so is a homomorphism, and let's say that we happen to have some information. We know that phi of 3 is equal to 5. What I want to do is find phi of 1. All right, so what do we do? Well, okay, so let's do it like this. So let's write phi of 1 equal to k. We know that it's some integer between 0 and 9. And now, right, so then, what do I want here? Right, 5 is equal to phi of 3, which is equal to, well, let's see. If phi of 1 is equal to k, that means that phi of 3 is equal to k plus k mod 8. Mod 10. So phi of 3 is equal to 3k mod 10. And so we need to solve this equation. 5 equals 3k mod 10. Okay, so let's just, now we can just kind of eyeball it. 1, no, 2, 3, 4, 5, 15 mod 10 is 5. Oh, so k equals 5 is the solution. Okay, so all we use here is the fact that we have a homomorphism, and so phi of 1 equals the k, then phi of 1 plus 1 plus 1 has to equal k plus k plus k. And next example. Okay, so we've been looking at homomorphisms from Z to various other groups. Now let's look at finite cyclic groups as our domain. So how many homomorphisms do we have? And we're going to go from Z16 to Z12. Okay, now what does the universal mapping property tell us? So if phi from Z16, or let's say this a little bit better. What do I want to do? Right, so if phi from Z16 to Z12 is a homomorphism, then what do we know? Okay, so a homomorphism from a cyclic group anywhere is determined by where it sends its generator. So what we need to do is say something about phi of 1. Right, so then phi of 1, whatever it is, raised to the 16th power has to be the identity. Now remember, in this case, because we're doing, or we're in an abelian group, it's really 16 times phi of 1 has to equal 0 mod 12, right? And so let's just write down the choices for phi of 1 and see if they satisfy this property right here. So choices 4, phi of 1. So it could be 0. And so then you ask the question, is 16 times 0 equal to 0 mod 12? Of course, the answer is yes. 1. So let's see, is 16 times 1 equal to 0 mod 12? No. How about 2? 16 times 2 is 32. Mod 12 is not 0, so there's a no. How about 3? 16 times 3 is 48. Mod 12 is 0, so yes. How about 4? 16 times 4 is 64. Mod 12 is not 0, so we get a no. 5, 16, 16 times 5 is 80. Mod 12, no. The next one is 6. That would be what? I don't know what 16 times 6 is. 16 times 6. Oh, 96. Mod 12, yes. And so we're just kind of go down the line. Who else do we have? So there's 7, 8, 9, 10, 11, and 12. And you can check. We're going to get a no, a no. Let me just be careful here. All right, it goes yes, yes. Oh, no. It goes no on 7. 8 is a no. 9 is a yes. No, no, and then, oh, there's no 12. So how many homomorphisms are there? Well, they correspond to our choices that satisfy the conditions of the universal mapping property, and so those are going to be those right there. So there are exactly 4. Right? The ones for which the output satisfies the condition that we have in the universal mapping property. So this tells us how many homomorphisms there are. How many are onto? The answer here is 0, right? Why is that? Well, if it's going to be onto, then phi of 1 has to be a generator of Z12. And if you notice, none of these, right, 0, 3, 6, and 9, none of those are generators for Z12, so none of them are onto. So just kind of as a extra note, right? You can make a note for yourself, or I guess I'd write it down. So note, none are onto. Okay, so let's do one more example here. So let's let, I'm going to go from Z20 to S4. So let's let phi from Z20 to S4 be defined by. So remember, I need to send 1, a generator of Z20, to somewhere. So let's be defined by phi of 1 equals 1, 2, 3, 4. So I want to send it to that 4 cycle. Now, this is going to work, right? This will give us a homomorphism as long as phi of 1 raised to the 20th is equal to the identity. And so if you notice, this element has order 4, so definitely raised to the 20th gives us the identity. So by the UMP, this defines a homomorphism. And now what I'd like to do, I guess I'm just going to do a couple pieces here, so, or a couple parts. So part A, I want to compute phi of 5. And part B, I want to find the kernel of phi. So part A, compute phi of 5. Okay, well, we know that phi of 1 is equal to 1, 2, 3, 4. So that means that phi of 5 This is 5 applications of the operation to 1. 1 plus 1 plus 1 plus 1 plus 1. That has to equal 1, 2, 3, 4 raised to the 5th power. Because 1, 2, 3, 4, that has order 4, this is equal to 1, 2, 3, 4. And then for part B, find the kernel of phi. Okay, so the kernel of phi, that's going to be the set of all, let's say, sigma in S4. No, it's not. It's going to be the set of all, what am I talking about? It's the set of all k in Z20, such that phi of k is equal to the identity permutation. Now, let's see. So we would need then, right, our formula for phi of n, right? If we take something from Z20, plug it into phi, right, take n, we can figure out exactly what it is from this formula right here. So phi of n is equal to 1, 2, 3, 4 raised to the n. We need this to be equal to the identity. And so when is that going to happen? It's going to happen when n is a multiple of 4. And so what we get then is 0, 4, 8, 12, 16. That's equal to the kernel of phi. I'm going to end with just a little bit of terminology. All right, and this is going to be the end of the chapter. We'll start a new chapter next time. Yeah, terminology. Terminology. So, a homomorphism is a, and here's our choices here. So it's let's start with monomorphism. Oh, you know what? Let me give this a name. So homomorphism phi is a, and so there's a bunch of fun words here. Monomorphism if phi is 1 to 1. So that's the term that we give to a 1 to 1 homomorphism. It's called a monomorphism. It's an epimorphism if phi is onto. All right, so an onto, a surjective homomorphism is called an epimorphism. It is, of course, called an isomorphism. We already know this. Right, it's an isomorphism if phi is 1 to 1 and onto. Right? So if it's both a monomorphism and an epimorphism, then it becomes an isomorphism, or is an isomorphism. And then there's a couple more. It's an endomorphism if phi maps from G to G. So in the case that we have a homomorphism whose domain is equal to the codomain, then we call that homomorphism an endomorphism. And then one more. It's an automorphism if phi is an isomorphism and an endomorphism. Endo. right? So an isomorphism from G to G, that's called an automorphism. Now here's an interesting fact. I want to call this, let's call it a fact. Check this. If G is any group, then the set aught G of all automorphisms of capital G is a group under composition. So that's interesting. Take the set of all isomorphisms from one group to another, and it turns out that you can form a new group called aught G, right? The group of automorphisms from G to G, right? So that's, well, how do you want to capture, what does that mean? It allows us, and we'll see this a bit later on, so the study of the automorphism of the G somehow captures the symmetries of the group itself, right? So there's one way to think of it. And let's end with this example right here. So let's let G be any group. And let's take an element, and let little g be an element of capital G. Now, if X is in, I want to say this, if X is in G, let's see, actually I want to say this a little better. If X and Y are in G, and Y is equal to G X G inverse, then X and Y are called conjugate. So then X and Y are said to be conjugate. All right, I know we're working an example, but I've got a definition built into my example, right? So if you have two elements of the group that can be expressed in this form right here, right, where one of them can be written as G times the other one times G inverse, then you say that the elements are conjugate. Now, let's define, I'll write this as phi sub G from G to G by phi sub little g of X is equal to Gx G inverse. This operation right here, Gx G inverse, that's called conjugation. Now, it turns out, so I'll just say check, that phi sub G is an automorphism of capital G, and it's an important one. It's called, right, so called an inner automorphism. So what this tells us then is anytime if we have a group G, we can create automorphisms by doing this conjugation operation. And every time I take a new G, I get a different homomorphism, right? Put a little H here instead, then we'd have HX, H inverse, right? That gives us a different automorphism, right? So this is a special type of automorphism. There are other types of automorphisms, right? Here's one type called an inner automorphism. Okay, so that's a good place to stop. That's the end of chapter, what chapter are we on? 13? I don't remember. Oh yeah, chapter 13. You don't really need to see me page around to figure this out. Anyways, we will see you next time. Okay.